Hello everyone, I'm Li Tingshi. I was a visiting student in CanmetMATERIALS Canada 2 years ago. Now I'm working in China Automotive Technology and Research Center. It's such a pleasure for me to share my work with you today. My topic of my presentation is about the effect of specimen configuration and notched angle on fatigue behavior of dissimilar resistance spot welds of AA5754 aluminum alloy to high-strength low-alloy steel. Multi-material solutions has become commonplace in the automotive industry. But when joining dissimilar materials, such as aluminum to steel by resistance spot welding, a thin layer of brittle intermetallic compound forms at the interface and dominates mechanical behavior of the joint. So in present work, we welded 1.1 mm thick AA5754 aluminum alloy to 2 mm thick high-strength low-alloy steel sheets using multi-domed electrodes with aluminum connecting to negative or positive electric polarity and multiple solidification weld schedules to achieve acceptable static joint strength. Tensile shear and coach peel specimens were welded and tested. The left three figures are macro cross-section of A5754 aluminum alloy to itself and aluminum to HSLA steel with aluminum connecting to positive electric polarity and negative electric polarity. The weld nugget diameters in aluminum to steel spot welds are around 7.5 mm, which are larger than that of aluminum to itself. From the cross-section views, we observed that asymmetric notched angles formed in aluminum to steel stack-ups regardless of polarities. Here are the results of thickness of intermetallic compound layers and micro-hardness of the cross-section. Both stack-ups exhibited intermetallic compound layers less than 3 micrometers in the weld nugget periphery. As can be observed from the TEM results, the same intermetallic compound distribution was observed regardless of positive or negative electric polarities. That is to say, let's see, a needle-like iron aluminum 3 adjacent to the aluminum sheet and a tongue-like iron 2 aluminum 5 adjacent to the steel sheet. After the macrostructure characterization of the intermetallic compound, we used mini-shear specimens to test strength of intermetallic layer formed at the interface of the aluminum to steel welds. The shear strength of the two kinds of stack-ups is higher than 60 MPa, which is dominated by intermetallic compound layer thickness of the weld nugget periphery. Here the arrow bars represent one standard deviation. Let's see the maximum tensile loads. Here are the maximum tensile loads of tensile shear and coach peel specimens with acceptable tensile peak loads. In addition, the aluminum steel resistance spot welds have greater, let's see the two bars, they have greater average maximum tensile loads than the aluminum resistance spot welds. This is due in part to the larger aluminum nugget diameters that develop in aluminum to steel welds as compared to the smaller aluminum resistant spot weld nugget diameters. Load-controlled fatigue tests were conducted for tensile shear and coach peel specimens, and the results show that the fatigue life is longer in the aluminum to HSLA steel spot welds than that of aluminum to itself. And all of the fatigue life have a high fitting coefficient. After the fatigue fracture, we also observed the fracture modes. In tensile shear specimens, pull-out fracture was observed at the high load levels, and interfacial fracture was observed at lower load levels. In coach peel specimens, all of the fatigue fracture modes are pull-out or eyebrow at all load levels. And then structural stress range is calculated based on Rupp's structural stress model. This model only considers weld nugget diameter and sheath thickness. Using this model, we got this result, and it reveals that all fatigue life data points from both the tensile shear and coach peel configurations fall onto a single master curve with fitting coefficients around 0.8. This indicates that the weld nugget diameter is the controlling parameter for the fatigue life. We noted that there are no shoot angles in aluminum to steel stack-ups, so we use finite element analysis to calculate the maximum principal strain of the aluminum sheet with different no-shoot angles. And the results show that the less maximum principal strain occurs in the aluminum sheets with a larger no-shoot angle. So the longer fatigue life in aluminum to HSLA steel is because less maximum principal strain occurs in the aluminum sheets compared to aluminum joint to itself. Let's see the conclusions. We welded AA5754 aluminum alloy to HSLA steel successfully using multi-domed electrodes and multiple solidification weld schedules. And then the fatigue life is longer in the aluminum to steel spot welds than that of the aluminum to itself spot welds. The structural stress analysis revealed that all of the fatigue life data fall onto a single master curve, which indicates that the weld nugget diameter is the controlling parameter of the fatigue life. Finally, the finite element simulation, considering material inhomogeneity in the weld, further confirms that a large no-shoot angle at the weld nugget is beneficial to yield longer fatigue life, as less maximum principal strain occurs in the aluminum sheet. Last but not the least, we are grateful for the financial support from Canadian Federal Government's Energy Innovation Program, Office of Energy R&D, Mission and Innovation Energy and User Program, Natural Resources Canada, GM Canada, and CanmetMATERIALS. And also we are grateful for the technical support from Jieliang, Babak, and Mark Gassing at CanmetMATERIALS. Here is my email and telephone number. That's all my presentation. If you have any questions, you can contact with me. Thank you.